Hi, we are Team 23055, and our project was to determine the efficacy of the lightning protection garments developed by Zoltar Technologies, a personal lightning protection company. I am Abby, the team lead, and I'm a biomedical engineer.
Hi, I'm Riley Cowling. I am the procurement lead and I'm an electrical engineer.
I'm James Gregory and I'm a biomedical engineer.
I'm Sebastian, I'm an electrical engineer.
My name's Victor and I'm a biomedical engineer.
Lightning is an electrical discharge caused by the buildup and release of electrical charges in the atmosphere. This discharge typically occurs between the negatively charged bottom of the cloud and the positively charged ground below. The ionization process creates a channel of charged particles which generates an electrical current that can heat the air to temperatures of 30,000 Kelvin, producing a bright flash of light. Lightning can carry hundreds of millions of volts and tens of thousands of amps of current, making it extremely dangerous to humans.
When lightning strikes the human body, the current from the strike automatically looks for the pathway of least resistance to the ground. This causes the human body to have an entry point and exit point to appear. With no protection, the current will pass through vital organs. Humans most commonly experience cardiac arrest, deep thermal tissue burns, nerve damage, or death.
The sponsor's garments include a modified raincoat and pants. The lightning protection modification is a discontinuous conductive path of Zell sewn onto them. The paths are supposed to redirect the lightning strike through a process called flashover. The sponsor hopes to prove the garments will protect vital organs by providing a preferable path to ground.
To effectively test the efficacy of the garments, we traveled to the DMB lab in Anaheim, which has an in-house Marx generator. A Marx generator is a type of electrical circuit that produces high voltage and high current pulses. The Marx generator is used by positioning the mannequin beneath the high voltage probe. The discharge due to the dielectric breakdown strikes the mannequin, either taking the garment path or the human path. The complex human body can be simplified and represented as a resistor.
This project had some very important requirements that had to be met. First, we have to mimic the human body to gather realistic data. The method of acquiring data has to operate at incredibly fast speeds and in the presence of dangerously high voltages. Lastly, we are constrained by the fact that our project will only truly have one day of testing in another state. This means our deliverable must be reliable and portable.
We were given the leftover materials from the previous team. Their design used a semiconductive tape to act as the human skin, which led to a heart resistor. This system was using a high-speed data acquisition device that failed on the first test, leaving them with no other way to give measurements. Learning from this, we set to work finding a feasible solution. To safeguard against failure, our team decided a modular approach would be best. This way we could incorporate a variety of different internal components.
Our ideal and most accurate measurement system relied on an FPGA board called the Eclipse Z7. In order to protect the FPGA board, we developed surge protection circuits using metal oxide varistors and TVS diodes. The system block diagram depicts the interconnections and protection scheme between the garments, FPGA board, and test circuit.
The majority of our requirements were met through analysis.
Ultimately, all of our analyses ended up showing that the duration of the strike is by far the most important aspect. This impacts how we measure it and the physical effects it has. With our plans made, the team got to work building out our designs.
This is the internal permanent circuit, for which we have developed a variety of inserts.
Now on the left corner, you can see the top of the mannequin's head, which is used as an entry point for the internal circuit, as well as the external circuit, which is considered to be removable. Like all teams, we dealt with unique problems that threatened to hinder or even prevent us from meeting our requirements. We ran into major issues regarding our FPGA development, along with many concerns regarding powering the device and providing it with adequate protection.
In our attempts to address this issue, we encountered layers of miscommunication that ultimately threatened to jeopardize the success of the project, as we thought we had access to DNB lab equipment which would not actually be relevant to our tests. Thanks to our team's design approach, we still managed to deliver a working system with fuses being our main method of measuring current, and a high-speed camera providing visual data.
Whoa.
Now, the videos and pictures are interesting, but it can be hard to tell what is actually happening here. I want to highlight these three regions. These points being lit up are indicative of the garment path being taken. For comparison, this is what it looks like when the path is not taken.
In this more detailed view, on the left, we see that when we close the human body circuit, the lightning takes that internal path. This meant the design of the garments was flawed. This point is made more clear in these photos using a hat instead of a hood. This depicts the lightning striking our entry point to our internal circuit, but it still jumped to the garments because of the better path to ground. When we close the circuit, there is a resistive path mimicking the human body in series with a fuse. Initially, there were concerns about how the fuses would perform in these conditions. But over the course of 40 tests, we demonstrated that the fuses were an effective method for obtaining a crude form of current measurement that, along with visual data, allowed us to confirm the redirection of a lightning strike with small alterations made to the sponsor's garments. So, we successfully met the requirements, but had not fully solved the problem. By no means did we fail, as we have gone farther than those before us and learned a great deal. Success is not a straight line, and the many ups and downs of this project have provided us with the opportunities to grow as engineers and as individuals. To begin our recommendations for our sponsor, we'll start with the human body. Initially, simulating the human body was not a top priority, but moving forward, we suggest that this becomes a bigger focus, and we will provide details on how to improve our circuit designs to incorporate this.
From all the tests performed, we can conclude that flashover ionization is not a reliable design for these garments. Instead, a direct and continuous path is required. We will be providing our sponsor with design adjustments that we think will address this issue. Finally, electronics, which we unfortunately did not implement in our final design. We strongly encourage that digital measurements be explored further in future development. EM shielding and surge protection are feasible concepts, and our team has laid the groundwork for that and the FPGA device capable of getting the necessary measurements.
Thank you for your time and attention today. We hope our presentation gave you a clear understanding of the problem and our approach. We're happy to answer any questions and appreciate your feedback.